Okay, so what I'd like to do in this video is just to continue on with this idea of conservation of mass. So conservation. B-A-T-I-N of mass. And also then as well, I'd like to talk about balancing chemical equations. So balancing chemical equations. Okay, so let's have a look at this picture here. So what we have a candle and it's put on a balance, a mass balance, and the candle's lit, and then we just observe what happens. Now, what's going to happen as time goes by, the mass is going to reduce. The mass is going to go down. So this number is going to gradually drop. Now, this idea of the conservation of mass, if we remember, states that when a chemical reaction occurs, the total mass of the reactants is always equal to the total mass of the products. Now, if we think about so what we have here, so we have a chemical reaction. So we have a reaction that's going on, or a change that's going on. So let's think about that and let's write that down as a chemical equation. So if we remember with a chemical equation, so you have what are called the reactants. Okay, so you have reactants. Reactants, they react. There's some kind of a change. So there's a catalyst, which is something that starts this change process happening. So you have a catalyst. So catalyst, and then you have the reactants, and then you have what are called products. So you get some kind of you get the starting off material, you get a change process that happens that's started by a catalyst, and then you get the end products that are produced. So if we think about the candle burning then, so what are the reactants and what are the products? So we can say that, so what do we have? So we have wax. So we have wax. So think about, so this here is wax, okay? And then there's a wick in it. And if you think about then so the candle is in the air, okay? And if we think about it in the air, then you have billions and billions and billions of oxygen. Oxygen molecules. So OXYG, okay, oxygen. So what's going to happen is, so you have wax plus oxygen. So these are your reactants. Okay, so these are the two things that are reacting with each other. You have the solid wax reacting with the gas oxygen, or O2, in the air. And these come into contact with each other in the presence of heat. So you have this reaction. So it goes in this way. The catalyst is going to be heat. So the flame in here is heat. Okay, and that's the catalyst. And then you're going to get like what's going to come out. So you're going to get all of this going in, a reaction happening, and then you're going to get coming out. Then you're going to have the products, which are carbon dioxide. Okay, carbon dioxide, so it's CO2, and so it's carbon and oxygen, plus water vapor. Which is just water, H2O, but in its gas form. So think about water can exist as a solid in ice, a liquid as in water, and then it can form as a vapor or a gas. Okay, so think about it in gas form. So you have oxygen here, so just O2. So it's just two oxygen atoms joined together. And then you have wax, and wax is what's known as, so they're called hydrocarbons. So basically they're made up of carbon and hydrogen. Now there's a lot of carbons and a lot of hydrogens just all attached together, and that's essentially what makes up wax. Okay, so you get these reactants reacting with each other, and then you get the products that are produced as this change process continues on. Now, what's actually happening is, if we think about this, but why is the mass conservation of mass? So this reaction happens, and we make this observation, and the mass is actually dropping. So the mass it seems to be disappearing, and it doesn't seem to be being kept constant. Let's say so. The mass of the reactants and the mass of the product, looking at this, it just seems to drop. So how do we explain that? Like, what can we say, and how do we explain that one? Well, if we think about, like, just very briefly what's happening. So if we have wax, okay, and it's a solid. Now, if we think about it as a solid, so remember particle theory. So we can think about the hydrocarbons, or the stuff that makes up the wax, as these tiny little particles, which we call atoms. Okay, and they're all, with a solid, what happens is these particles are packed really, really closely together. And that's what gives it the characteristics of a solid. Then if we think about the oxygen, so imagine then we have the oxygen. So these are gases. So what does that mean? If you think about it from a particle point of view, these particles are all spread out all over the place. Okay, and they're able to move around and move across each other. And they're able to come down here and bounce off the solid wax and bounce back up again. Okay, so they're able to move around. So it's in a, so this is, so if you like, this is solid, and the oxygen is in gas form, or should I say gas state. So what happens is then when you get this heat that happens here in the middle, okay, so this is like the catalyst. Remember the catalyst that starts the reaction. What happens is a change process starts to happen, and the solid particles that are inside here, they start to melt, and they start to turn into a gas. And then when they turn into a gas, what can happen is the wax particles can come into contact with the oxygen particles, and they physically come into contact with each other. And then what happens is it starts this chemical reaction happening. And what happens then is you get carbon dioxide. So imagine I'll represent carbon dioxide just as pink here. Okay, so you have these carbon dioxide molecules. So as the yellow solids and the blue, let's say, gas particles come into contact, you get these new particles being formed, and so represented here in pink. And this is the carbon dioxide. Now, the carbon dioxide being a gas, it just moves away, it spreads off, it diffuses, let's say, out into the environment. And the same then with the water vapor. I can just represent it by a purple particle here. Okay, like this. So you get water molecules being formed, and they're also being formed as well. But again, because they're in gas form, what happens is they fuse, or they spread out into the environment like this. So you get this whole chemical reaction that's happening, and you can visualize this and think about it from a particle point of view. So as a result, what's happening is these particles, as they're being formed, they're spreading out away into the environment. And as a result of that, this mass is reducing. So it's like the packed particles that are inside here in the candle, okay, they're being converted, and then they're being moved away and shipped away from this solid body of the candle body. And as a result of that, the mass of the candle is reducing. Now, that doesn't mean that the conservation of mass law does not apply. So what you'd have to do to observe the conservation of mass laws, somehow, if you were able to, let's say, gather up, so as you have carbon dioxide and water vapor being produced here within this reaction site, if you were able to, let's say, just gather them up, okay, and you were to weigh them, okay, so imagine you were to weigh, like, these are all of the CO2 molecules, and then these are all of the water molecules. If you were to measure them up and then compare it to the mass that you started off with, they will equal each other. So what will happen is you will get, So the reactants mass, okay, so that would just be the mass that you started off with, is going to be equal to the product mass. Okay, so just to think about it in really simple terms, like let's say if we started off with, if the wax had a mass of, let's just say 1, and the oxygen had a mass of 1, then the mass of the reactants is going to be 1 plus 1, which is equal to 2. Okay, so that's the starting mass you start off with. So therefore, the mass of the products that you end up with, so they have to equal 2. So let's say this might be 1 and this might be 1, so they have to be equal to 2. So it's basically what, like it's 1 plus 1 is equal to 2. So that's just, now like here we're starting off, we can see it's a mass, if we read the balance, it's 463.92 grams. But I'm just trying to kind of simplify it here. Basically what we're saying is that whatever mass we start off with in the reactants, in the things that react together, they have to be equal in the products. So it's like the mass, you know, the atoms or the particles that make up like the reaction, they don't just disappear. What happens is they are conserved, and you have a conservation of mass. So they're just, it's like saying, so the solid wax particles are all arranged in a particular way, let's say as a solid, but then when they come in contact with the heat from the flame and they then react with the oxygen that's in the air, they just get moved around and they get repackaged, let's say as, you know, carbon dioxide and H2O. So you have, like if you think about in wax, you have the carbon atoms and you have the hydrogen atoms. Well, those atoms get broken apart and they get rearranged and they get attached to the oxygen that's in the air. And then you have, so you can see here, some of like the carbon, for example, ends up attached to the oxygen like this, and you get this new product formed, which is carbon dioxide. And then the hydrogen, let's say that makes up the wax as well, that attaches to the oxygen, and you get, for example, water vapor. So it's just those particles that make up the mass. The particles give the mass to the candle that you start off with. They just get rearranged and repackaged, and they form these new. They form part of these new products that are formed. So it's just kind of that's what happens. Let's say in the case of when a candle burns. So I just want to look at this kind of reaction in a little bit more detail as well, just the burning of a candle, because there's so much chemistry and there's so much physics that actually happens in this process of burning the candle. So hopefully when you look at this and when you look at a burning candle again, let's say, you will think about this and you'll realize, you know, like the complexity of what's going on there. There's a lot of chemistry and there's a lot of physics actually going on in this process of just burning the candle. So if we have a look over here, so I just want to kind of look at this in a little bit more detail. So the process of like what actually happens when a candle burns. So you have a chemical reaction that's happening here. So here within the candle body you have the wax. Okay, so you have wax. And that's primarily, wax is made up of carbon. So carbon and hydrogen. Okay, it's just all attached together in particular ways. So it's as a solid. So imagine like all of these, if you think about the particles, if you're to look in here, the particles are all packed really close, tightly together. You have then, let's say, the wick of the candle. So you have this wick here, and you normally light the wick. And what happens is that produces loads of heat. Now this burning here, it can burn up to 1000 degrees Celsius. So just to kind of put that into context, like how hot that is, you have, if you think of a boiling kettle, when you boil your kettle to make a cup of tea, when the kettle boils, it's up on 100 degrees. So think about how hot that is. Like if you were to put your hand in, like if you were to put your hand anywhere near, you would feel the heat that's coming off that. You'd feel the energy. Well, if you multiply it, so imagine that 10 times that. That's how hot it burns, let's say, within this space, within a candle. So what you get is you get this, you light your wick and it produces heat. And this heat then, it starts to make the particles that make up the wax it gives them energy. They start vibrating and they start changing they go from a solid into a liquid, and then what they do is they move into a gas. So it's like the particles, let's say in a solid, they're really close together. In a liquid, they have a little bit more space, but then in a gas, they're actually spread out and they're moving away from each other. So what happens is you get this wax, it starts to melt, and it starts to move up the wick, okay, into the flame that's produced here when you light it. So you get this movement of this liquid hydrocarbons or wax. It starts to move up here, and it moves up by a process of capillary action. And it's capillary action. I'm not going to go into it in too much detail, but capillary action is the same process that if you take a tree, for example, it has to soak up liquid from its roots all the way up through its trunk, right out to the leaves that are in the plants. And it does this it's a physical process of capillary action. So it's a physical process that happens. If you think about animals, we have to move liquids through our body, and we use like a pump, like the heart, to pump liquids around our bodies through our veins, whereas plants, for example, use capillary action. Now, a candle then as well, you also use capillary action to make this melted wax move up the candle wick, and that's what starts to happen. So this liquid wax moves up here, and it moves into the flame, which is up on 1,000 degrees Celsius. So this is like the fuel. The wax is the fuel that keeps the flame in the candle burning. So what happens then is you have the flame heat vaporizes the wax. And remember, wax is made up of these carbon and hydrogen atoms. And it vaporizes it into molecules of hydrogen and carbon. So all it's basically saying is that this carbon and hydrogen molecules that are attached together, they're split apart. So imagine your purple are your carbon particles, and then let's say this here is your hydrogen particles. So what happens is they split apart and they're vaporized. So they are. So you get the vaporized. So then these carbon, so you have carbon, let's say particles all dancing around or moving around here within the flame, like billions of them, and you also have hydrogen as well, let's say dancing around, moving around here within this flame. So you get this happens here. The particles break up, let's say here, okay, and then they form like carbon and hydrogen particles, let's say within the flame. And then what happens is, so you have carbon particles ignite and become incandescent. So it's like the carbon particles, they get so much heat from this 1,000 degrees that's coming from the flame that they glow basically, and they give off light. So they give off this light that we see. And this light that's given off, this is energy as well. And we use that energy to light the room, for example. But there's also lots of heat as well. There's loads of heat being produced as well, this energy that's being produced. So the carbon particles ignite and become incandescent. So you have, let's say, all of these broken up carbon and hydrogen particles that are moving around, let's say, within this space here where it's all being heated up. And then what happens is outside here you have oxygen, O2. So imagine you have all these oxygen particles. It's in the air, for example. And what happens is they kind of get sucked in here into this process. And what happens is they then start to fuse or connect or bind with the broken up carbon and hydrogen. And then what happens then is this process spits out then the products. So you have CO2, carbon dioxide, and then you have H2O, you have water vapor as well. So that's kind of like what happens. So if we have a look here, so this kind of just goes through it in a little bit deeper as well. So you have this burning of the flame, you have oxygen being sucked in here, you have the wax being melted and turned into like vaporized, and then everything here then, so you have oxygen, you have fuel, and then you have heat. So what you do is you get this flame and you get fire being produced. So the heat rises, so it moves up into the air, and what you get then is you get like carbon dioxide. So you get carbon dioxide being spread out into the room, and then you also get steam as well, which is H2O. Steam is just H2O that's heated up and it's in gas form. So it's in gas form. So this is really interesting. And what's also really interesting too is that you get this characteristic flame, which is like a teardrop flame. So it's a particular shape. Now the reason it's that shape is because of gravity. So what you have here from the body of the Earth, you have gravity, and it's a force, and it's pulling down. So what's happening is the particles that are the carbon particles that are white hot and glowing, they're moving up in this direction. They're moving up the way. So they're moving up, and what happens is gravity. Okay, so this is just starting to work for me now. So gravity. Okay, bear with me 1 second. So gravity is so these particles are moving up because of the heat. Okay, they're rising up into the air. But then what's happening is gravity is having a force, and it's pulling it back down in this direction. So what ends up happening is you get this whole body here. It kind of stretches. So it's being pulled up this way by the heat rising, and then it's being pulled down this way by the gravity as well. So what you get is you get this teardrop shape where this chemical reaction is actually happening. If you were to go into space, for example, in the International Space Station, and I'll play a video at the end of the lesson just to kind of show you this. If you were to light a candle, for example, in the International Space Station where there's zero gravity, the candle shape will be something like, it'll be kind of like circular like this. It'll burn in a circular shape like this. And the reason being is because you don't have gravity acting on it and pulling it down like that. Okay, so that's just the conservation of energy, and then it's also conservation of mass, and then we're also looking at just like the chemistry and what happens, let's say, when a candle actually burns. So now what I want to talk about is just balancing a chemical reaction. So we're going to move over here and just have a look at this. So again, what we're looking at here, so this is, again, these are just it's a chemical equation. So just a little bit more detail now in this. So what we have then is so the wax and the oxygen. So these are our reactants. And then we have our carbon dioxide and our water, which are our products. Now we can see in the chemical equation, it gives a lot more detail. So we can see here that we have in wax is made up of carbon and hydrogen. So you have 25 carbon atoms and 52 hydrogen atoms, and they're arranged, they look something like this. So they're arranged in this kind of physical structure. So it's like a repeating structure. So this is carbon, and then these little white things are hydrogen, and it's arranged in this physical structure that just keeps repeating, going on and on and on. And that's like essentially what candle wax is. It's in this form. Then we have oxygen. So we see that oxygen exists as a molecule of oxygen like this, and it's just basically two oxygen atoms connected together by this bond in here, which is a covalent bond. And then you have your products. So again, the carbon, the hydrogen, and the oxygen. When this reaction happens, when you have heat from the flame of the candle, these atoms, and you can think about them as particles, for example, they just get rearranged and into different what are called products. So you have carbon, you have oxygen, that's CO2, carbon dioxide, and then you have hydrogen and oxygen. So again, the hydrogen is coming from the wax, the carbon is coming from the wax, and then the oxygen is coming from the air. And what happens is these just rearrange they rearrange, and you get what are known as the products being formed. So what we want to do is just thinking about the conservation of mass. So whatever we start off with, so however number of atoms of carbon and hydrogen and oxygen that we start off with in relation to at the start of the reaction, they have to be be balanced, let's say, in the products at the end of the reaction. And that's what I want to talk about now, what's known as balancing chemical equations. So what we can do is we can draw a table like this, and on one side we have the reactants, okay, and then on the other side we have the products. And we can draw a line here like this. So we can, like, what we're interested now in looking at is we want to look at the individual atoms that we have on the left and the right. So if we think about what atoms have we got here on the left and the right, well, we have carbon. So we have carbon, which is represented by C on the periodic table. We have hydrogen, which is represented by H. And then we have oxygen, which is represented by O. Okay, so carbon, hydrogen, and oxygen. And then on the right hand side we have exactly the same. We have carbons, we have hydrogens, and we have oxygens. But if we look at this, the number of carbons that we have on the left hand in the reactants is not matching up to the number of carbons and hydrogens that we have in the reactants. So what we want to do now is balance the equation. So the first thing we have to figure out is what do we have. So let's look at the carbons. So how many carbons have we got on the left hand side? So we can see here, if we look at this chemical equation, we have this little number here, 25. It's a subscript to the C. So that tells us that there's 25 carbon atoms. So we have carbon, we have 25 of them. Okay. If we look at hydrogen, the same thing. We have this little number here, 52, and that tells us the number of hydrogen atoms that we have. So hydrogen, so we can see them here. So hydrogen, we have 52. Okay, so we have 22 carbon atoms, 52 hydrogen atoms. If we have a look at how many oxygens we have, we can see here the number of, we have this little small subscript number, which is 2. That means that there's 2 oxygen atoms bonded together, just like this. We have 2. The red spheres here represent an oxygen atom, and there's 2 of them bonded together. So we have 2 oxygen atoms. Now if we go over onto the right hand side and look at the reactants, how many carbon atoms have we got? Well, if we look here, it's saying that we have one carbon atom, which is in the carbon dioxide molecule, so we have 1. If we look at the oxygens, how many do we have? So we can see here within the carbon dioxide we have 2 oxygens. So we have two oxygens here. So I'll just represent this as a 2 here. Plus we also have 1 oxygen here. So you can see in the water molecule we have 1 oxygen, and you can see here. So this is the way. So this is an oxygen atom, and it's bonded to 2 hydrogen atoms that we can see here. And that makes up the structure of water. So we have 2 oxygens coming from the carbon dioxide, and then we have 1 oxygen coming from the water molecule, like so. If we think about the hydrogens, then how many hydrogens have we got? So we see that we have this little subscript here beside the hydrogen, and that means that we have 2 hydrogens within the water molecule, and this is what they look like. So this and this, these are hydrogens bonded to oxygen, which is here. Okay, like this. That's the way they're arranged. So how many hydrogens have we got then? We have 2 hydrogens. So we can see here that there's clearly an imbalance going on. So we're starting off with 25 carbons and we're ending up with 1 carbon. Okay, so it's not balanced. We have 52 hydrogens and we end up with 2, and we have 2 oxygens and we end up with 3. So 2 plus 1 is equal to 3. So what we have to do now is we have to go about balancing these. So what we can do is we can increase the number of, for example, carbon dioxides or waters that we have. So what we do is we look at the carbons first, and we see here that we've 25 on the right hand side, or on the left hand side in the reactants coming from the wax, and we have 1 on the right hand side in the reactants coming from the carbon dioxide. So what we have to do is we have to increase this. So if we've 1 here, so we need to multiply this by, so we need to multiply it by 25. So that will give us 25 carbons. So what does that look like? So the carbon is coming from the carbon dioxide, so we need 25 of these. So we can put this 25 in front of the CO2 here, like so. So that means we've 25 carbon dioxides here. Now, if we increase the carbon dioxides, we have to increase here as well. So remember, each carbon dioxide has 2 oxygen atoms, so this number here is going to increase. So it's going to be 2 multiplied by 25, which will be equal to 50. So now we're going to have this number here is increased to 50 plus the 1 oxygen that we get from the water molecule, and that's going to be equal to 51. So now we have 51 oxygens on the right hand side. Okay. So what we have now is, by doing this, we have the carbons are balanced. So we've 25 on the left and we've 25 now on the right. So if we focus on the hydrogens then, so we've 52 here and we have 2 hydrogens on the right hand side. So we have to increase this number here. So how do we do that? So if we think about, if we have 52 hydrogens on this side and we have 2 on this side, the 2 hydrogens are coming from the water molecule. We need to increase this by 26. So 26 and 26 is 52. So we'd have to multiply this by, 26. That would be equal to 52. So what does that look like? We have to multiply this water molecule by 25. So 25 here. So now we have 25 water molecules. So that will balance the hydrogen. So we have 25 hydrogens. So that will give us 52 hydrogens on the right hand side. Now if we do this, it also increases this number here, the number of oxygens. So what this is going to increase, it's going to be, you're going to have 50 oxygens coming from you're going to have 50 oxygens coming from the carbon dioxide. Okay, so that's the 50 there. But now we're increasing, because we've multiplied this by 25, we're increasing the number of oxygens we're having here as well by 25. So it's going to be 50 plus this extra 25 oxygens, which has come from here. So that's going to change this number here. It's going to change the overall number of oxygens on the right hand side. So it's going to be equal to 50 plus 25 is going to be equal to 75. So now we have 75 oxygens on the right hand side. So now we need to kind of look over here and see. So we have the hydrogens balanced. So we've 52 on the left hand side here, and we have 52 on the right hand side. So they're balanced now. But now we have an imbalance in relation to the oxygens. So on the right hand side we have more oxygens now. We've 75 oxygens. So what we need to do is we need to look over here and balance that. So we've two atoms of oxygen coming from this oxygen molecule. So we want to increase this. So how can we increase it? So we can multiply this by, so if we think about 75, what's the half of 75? So actually, just looking at this, this here should be 26. So let's bear with me now. So this should be 26. It's actually 26 because we've multiplied it by 26. So this here should be 26. Oh. So bear with me now, 1 sec. It should be 26. And that would make this number here then 76. So sorry about that now. So this should be 76. So this is equal, so it's equal to 76. So if we think about it now, we have 76 oxygen atoms on the right hand side. So we need to increase the number of oxygens that we have on the left hand side. So 76 then, the half of 76, it's going to be, so I'll just cancel this, so 76 divided by 2, so that's equal to 38. So what we can actually do is we can multiply this by 38. And that's going to be equal to 76. So what we do is we are increasing the number of oxygens here by 38. So we're just putting this 38 in front of this, so that means we've 38 oxygens. So now we can see that everything is balanced now. So we have 25 carbons on the left hand side. So we have the 25 carbons here coming from the wax. And now we have 25 carbons on the right hand side. So we can see here that we have our 25 carbons here. We have 52 hydrogens on the left hand side, and now by manipulating this we have 52 carbons on the right hand side. So we can see here that we have increased this here as well, so 25. And then what we have, oxygens, we have 76 on the left hand side in the reactants, and we have 76 now on the right hand side. So what we can say is we can take this chemical equation here and we can rewrite it as a balanced chemical equation, and it would look something like this. So you have C25 H52. Okay, so that's our wax. So plus 38 oxygen molecules. So it's oxygen reacts with, so you need heat. And so this reaction, so let's say, will give us 25 CO2 or carbon dioxide plus 26 H2O. So 26 H2O. So this is what, so we've taken this here and we've just, through this process, we've balanced it. So this is what's known as a balanced chemical equation. So that's what we're saying is that one molecule of wax will react with 35 oxygen molecules, and that will produce 25 carbon dioxide molecules and 26 water molecules, and then it'll produce energy in the form of light and heat. That's, when the candle glows. So this is, and we'll do a few more of these as well, but this is just an introduction to balancing chemical equations. So what you're trying to do is get the same number of reactants, the atoms of the reactants, balancing with the atoms of the products that are produced as well. Okay, so hopefully that made sense, and so just have a look at it, and pause it as you need to and go through and follow through it. But that is conservation of mass, and then how to balance chemical equations. Okay, so thank you for listening.